Hi, folks. Today we're going to talk about metric spaces. And so, what is distance? That's the big question for the day. What is the distance between 2 points? And so, in Algebra 1, you learn the formula for the distance between 2 points. But in the real world, we know it's not that easy. For instance, how do you measure the distance between American River College and Sacramento City College? Well, it becomes a question of which freeway are you taking? Or do we want to measure this with respect to time? Or do we want to measure it with respect to space? How are we defining distance in that context? Would it be a straight line? Would that be appropriate in this situation? And so, this idea of distance, we all understand what we are talking about when we say distance, but how do we formalize it? And so that's what the idea of metrics and metric spaces are all about. It's all a way to formalize this idea, this structure of what it means to be a distance. So in analysis, this idea of distance is at the forefront. We call these distances metrics, and a set on which we can apply a metric is called a metric space. Metrics aren't the only way to measure distance, but it's a very structured approach. And so the idea is if we can show that there is some metric, one of these formal distances, then all of the rules that we have in play for metrics, which have been built for 150 years now, they are then available to whoever wants to use these rules. And so let's see if we can understand what this structure is. The simplest examples are the Euclidean metric, which you should already know from Algebra 1. The Euclidean metric, based on the Pythagorean theorem in R2, is just saying what the square root of the difference in the x's squared plus the difference in the y's squared. And so we always want to keep that idea of distance in mind. This is just the shortest distance between 2 points. But depending on the context, that might not be the distance which is most applicable. Before we get any further, though, we do want to mention something called the triangle inequality. The triangle inequality is something we've always known but might not have had a name for. So let's discuss it. Given a triangle in R2, it will always be the case that the sum of two sides will be greater than or equal to the third side. Always, always, always. And we can see this here. The distance for this length, x, plus this length, y, if we add those two distances together, we're going to get something which is more than this bottom one. The only case where it would be the same is where this distance x plus this distance y is equal to this distance z is if they're actually on the same line. And so that doesn't happen too often, but it does occasionally happen. And so this idea of the triangle inequality is something we are going to want to keep in mind as we're exploring these metrics, these distances. Whatever distances we come up with, we want to make sure they're satisfying this property. For real numbers, it's also the case. And so if you are taking the absolute value of x plus y, that's less than or equal to the absolute value of x plus the absolute value of y. And so that's a nice thing to know. And so let's come up with our definition. And it's a weird one, but if we take it bit by bit, we should be okay. And so consider a set M. Then we say D is a metric on M if it has the following property for all points x, y, and z in M. And so the first property, the distance from a point to itself must be 0. And so dxx equals 0. The distance from something to itself, there's no distance there. The next one is positivity. And so the distance between two different points is always strictly positive. And so the distance from point x to point y is greater than 0 whenever x is not equal to y. And hopefully this makes sense. If we're saying that two different points aren't the same point, we want there to be some distance there. The next is symmetry. This one gets us in trouble sometimes. So symmetry is the distance from x to y needs to be the same as the distance from y to x. And so if you are measuring something from a ruler, if you turn your ruler around, you're going to get the exact same distance. We would hope that would be the case, but honestly, with some things we're trying to measure, that's not going to be the case. And so we have to be cautious. The last one is the triangle inequality, and that's the one we just talked about. The distance between 3 points has to satisfy the triangle inequality. If it doesn't, then we can't say it's a metric space. The collection of set and metric, by the by, is called a metric space. And so that's what this idea is. We're trying to measure the distance between 2 points. If the distance from a point to itself is 0, if the distance from a point to anything else is always greater than 0, if there's symmetry, meaning the distance from A to B is the same as the distance from B to A, and if we satisfy the triangle inequality, then we can say that this is a metric. Let's look at some examples. And so our first example is going to be the real number line, which, it's real numbers. We know our numbers. And we're going to define D to be the absolute value of the difference of two values. And so the distance from X to Y is going to be the absolute value of X minus Y. This is a metric. And if you want, I've got the proof here, but let's just try and logic it out and see if it makes sense why this would be a metric. And so first things first, we want to make sure that the distance from some point to itself is going to be 0. Well, if you plug in any number and itself, so like 3 minus 3, yeah, you're going to get 0 there. If we are dealing with any other values, and so if these two values were not the same, then the distance between them is going to be greater than 0. We're dealing with 5 and 3. 5 minus 3 is 2. So that is greater than 0. If we did 3 minus 5, well, it's an absolute value, so it'll still be the same value, which is important for the third thing. We need to have that there is symmetry. And so we would want 3 minus 5 and 5 minus 3 to give us the same thing, which they do because of the absolute value. As for the triangle inequality, that one's always a little trickier to prove. If you want, I've got it written out over here. We won't stress that one for now. But we can show that this thing is going to be a metric. Let's do the distance formula. The distance formula is a standard example in R2, and it's something that most Algebra 1 students are required to memorize for some reason. So consider the Cartesian coordinate system in R2 and the standard distance formula. And so in this case, we would say point A is x1, y1, and point B would be x2, y2. Then we'd say the distance from A to B is given by x1 minus x2 squared plus y1 minus y2 squared. Or you could do x2 minus x1 squared plus y2 minus y1 squared. Because you're squaring it, you're getting the same answer. This distance formula is a metric, and hopefully you can see why. If you're trying to find the distance from one point to itself, you're going to get 0. If you're finding the distance from one point to anywhere else, well, you're going to get a number which is greater than 0. If you're trying to flip it, and so if we're going from negative 2,4 to 10,1, or if we're going from 10,1 to negative 2,4, that distance is going to be the same thing. And then it's also going to satisfy the triangle inequality. We modeled the idea of metrics after this example. We want metrics to have the same properties. And this is just the Pythagorean theorem. I mean, if we think a squared plus b squared equals c squared, if you solve for c, you get this distance. And so this is the defining example. We can take that one to higher dimensions if we really want to. And so in R cubed, or R3, the standard distance formula would be x1 minus x2 squared, y1 minus y2 squared, z1 minus z2 squared, add them all up and square root it. It's the same thing as the distance formula in 2 dimensions. The only difference is now we've got a third one. We could also go higher if we wanted to. If we wanted to go into 4 dimensions, well, we would need a new variable, but let's say it's w. We would just add a w1 minus w2 squared. And we can continue on into whatever dimensions we need. Technically, our distance X minus Y would also be meeting in this category, because if you take the square root of square root of X minus Y squared, that's the same as the absolute value. So now that we've got the general idea, let's go abstract. Let's see how weird these things can get. And oh, some of these metrics can get weird, but they have applications, and it all depends on what type of thing you're really measuring. And so consider the metric d on R given by this. And so the distance from x to y is going to be 0 if x is equal to y, and 1 if x is not equal to y. Let's prove that it's a metric. So we just have to verify those 4 different conditions. If you'd like to try it out on your own, give it a shot now. If you don't want to, let's look at the solution. And so 1 and 2 are trivial. And so we know that the distance from x to x is going to be 0 because that's how it's defined. And we know that if x is not equal to y, then the distance is going to be greater than 0. So we've got that. It's also easy to prove that the distance from x to y is the same as the distance from y to x, because if they're the same, it's 0, and if they're different, you get 1. The triangle inequality, in this case, it's not terrible. And so if the distance from x to z is equal to 0, then we automatically satisfy the triangle inequality. And so we're done. If the distance from x to z is equal to 1, then x is not equal to z. Well, that means that if we're going through some other point, then either we're going to get a distance of 2 or a distance of 1, which means we satisfy the triangle inequality. And so this thing is definitely a metric. The question becomes, why would we ever want to use something like this? And I mean, there are practical applications. What this is saying if you're staying still, that's going to not count as distance traveled. If you make any movement, that counts as one movement. And so what this discrete metric gives us is a way to bounce around values and count the number of bounces we take. For example, if we go from 1 to 7 to 3, then we would say the distance from 1 to 7 plus the distance from 7 to 3 would be 2, meaning we took 2 steps. You can think of it kind of like how a frog would jump around on the number line. When we think of putting binary operations together, this can tell us how many binary operations we are using. This is useful in computer science. The idea of error correcting codes in quantum computing is based on this idea. And so this discrete metric, it does have applications, even if it is a very weird way of measuring things. Oh, the next one's a good one, the taxicab metric, also known as the Manhattan metric. And so consider ordered pairs in R2 and define the distance formula to be the difference in the x direction plus the difference in the y direction, both under absolute value. Prove that this is a metric. Again, this one's not terrible to show, at least for the first few. Triangle inequality, it's always tricky. But if you're going from one point to itself, this is going to give you 0. Anything where the points are different, it's going to be strictly greater than 0. And there's definitely going to be the symmetry. Triangle inequality, there's the proof. It's a little bit messier. But let's see the visual for this, because that's really the fun bit of the taxicab metric. This is one we're more likely to use in the real world. And so the taxicab metric, also known as the Manhattan metric, measures the distance traveled in a grid-like city. And so thinking the grid to the right, the blue, red, and yellow paths are all taxicab distances. And so if we measured how many blocks we are going to get to our destination, that's the taxicab metric. The green one would be the Euclidean metric. And so that's the difference between the Euclidean metric and the taxicab metric. When we start thinking about how long it takes to travel from one position to another position, or distance between 2 cities or something like that, we're more likely to use something like the taxicab metric. And so we got to keep that in mind. This gives you a more realistic way of measuring distances for things which are structured in a grid. See also the pixels on a screen or seats in a stadium or anything with rows and columns. Next one's a weird one. Chebyshev's metric. And so consider the ordered pairs in R2 and define the distance as the maximum of either the difference in the x direction or the difference in the y direction. And so whichever one is greater, we are going to define that as the distance. And so 1 and 2 are trivial again. And if the 2 points are the exact same point, distance is going to be 0. And if they're not the exact same point, then the distance is going to be greater than 0. We can also show symmetry because we got absolute values and differences. And so we know that if we switch the x1 and x2 and we switch the y1 and y2, we're going to get the exact same thing. The triangle inequality, once again, tricky to show, but if you want, there is the proof. And so now what's the value of Chebyshev's metric? Well, there's a few important things that happen with it. One is sometimes the Euclidean metric might not be so nice. What we know about the Chebyshev metric and the Manhattan metric is that the Euclidean metric is always going to be between the two of them. And so if we can figure out something for the taxi cab distance, and we can figure out something for the Chebyshev distance, then we can be guaranteed that the Euclidean distance is going to be between the two of them. And so Chebyshev's metric, also known as the chessboard metric, and we'll see why in a minute, gives us a way to model what squares look like in a plane. Consider to the right a graph of points which are distance 1 away from the origin in the Euclidean, taxicab, and Chebyshev metric. Our Euclidean will always be bounded between the Chebyshev and the taxicab distances. And the Chebyshev distance, in particular, gives us this nice square shape. So the reason why it's called the chessboard metric is because of what happens on a chessboard. Hopefully that makes sense. And so if we're thinking about the difference between these three, the Chebyshev works just like the king. And so the king can go 1 in any of the directions. And so that means that if you're trying to go from this position up here down to this position here, well, the king would only need 1, 2, 3, 4 moves in order to get there. The Euclidean norm would work more like an ant. And so going 1 left, right, up, or down is just going to be 1. But if you're going on the diagonal, that's actually going to be a square root of 2 distance. And so we can actually think of what the actual distance is between these two things. If you're going from this piece down to this piece, under the Euclidean norm, it's going to be a distance of 5. And then a taxicab is saying, well, what if you can only go left, right, up, and down? How many total spots do you need to go? And so without any diagonals, we would go 1, 2, 3, 4, 5, 6, 7 spots. There's also the discrete metric, which is interesting. If you wanted to do the discrete metric going from here to here, you would get 1, because really it works just kind of like teleporting. If you are jumping from this place to this place, that would be 1 move. And so the discrete metric would say that distance is 1. And so we can start to see how these different types of distances can measure different things. And we can, of course, do this in higher dimensions too. We already talked about what the Euclidean metric looks like in higher dimensions. Well, what do you think the discrete metric would be in 3 dimensions? It's going to be the same idea. It's going to be how many times are you jumping from one position to the next position? What about the taxicab? How would that work in 3 dimensions? Well, you would be adding up how you're going across in all 3 dimensions. And then the Chebyshev metric, well, that's going to be the maximum of the distance in the x, the y, and the z directions. It would be the same idea if we were to do it in 7 dimensions. At that point, it doesn't matter. We now have an idea for how all 3 of these different metrics work in addition to our standard Euclidean. Oh, so now that we have the idea of metrics and we know what graphs are, how can we combine the two? And so recall that a graph is a collection of vertices and edges. We can think of the vertices as a set, and the edges tell us how the vertices are connected. And so consider the graph to the right. It has 5 vertices and 6 edges. Is it possible to define a metric on the vertices of a graph which preserves the structure of the edges? So can we define distance on this thing? What would it mean to be a distance from 1 to 5? Well, one approach is to just use the length. And so recall that we actually have a definition for the length. The length of a path is the number of edges along the path. And so consider the graph to the right. If you're going from 1 to 5, that distance would be 2. If we are going from 2 to 4, well, that distance would also be 2 because we could go 1, 2. The distance from 1 to 1 would be 0. The only time you would get a distance of 0 is if you're going from a number to itself. And so it's easy to see that this meets the definition of a metric, and the graph itself is a metric space. What about a directed graph? Will directed graphs form a metric space? Well, generally, no, they won't. But let's see why. And so if a graph is directed, can we use the similar definition to define a metric? We can still define the length of a path as the shortest distance connecting 2 points while adhering to the directionality of the arrows, but we can't really define it as a metric because we're not going to have symmetry. In this case, if we're doing the distance from 2 to 1, that's going to be very different from the distance from 1 to 2, because 2 to 1 would be a distance of 1. The distance from 1 to 2, well, you'd have to go from 1 to 0 to 2, so it'd have a distance of 2. And so this does not mean that there are no metric spaces, just that we'd have to be more creative. If we really wanted to, we could apply the discrete metric in this case. You can teleport from any one point to any other point. That will technically be a metric space. But we don't necessarily need to have all of the properties of a metric space to still call something a distance. We can still measure the distance from 1 to 2 or from 2 to 1, even if we're not dealing with a metric space. It's just we have a lot of additional tools for metric spaces if we want them. How about in a weighted graph? And so suppose that we have a connected weighted graph with strictly positive weights. And so we will assume that we have positive weights, such as the graph to the right. We can define a distance d between 2 vertices as the smallest weight of a path between them. And so if we are looking at going from 0 to 3, the distance from 0 to 3 would in fact be 6. I know you see the 7 here, but that's not the shortest path from 0 to 3. To get from 0 to 3, we go from 0 to 1, then to 2, and then to 3. That would give us a 3 plus 1 plus 2 would be a total of 6. The distance from 4 to 1 would be something similar. So to get from 4 to 1, well, we would probably go 3 to 1, and 3 plus 2 plus 1 is going to give us 6 as well. And so be careful, the distance from 1 to 3 is not 4. And so even though you see the 4 here, the distance from here to here is actually 3. 1, 2, 3. And so this distance does describe a metric. You might have trouble seeing it because it really feels like the triangle inequality isn't in play because 4 is more than 1 plus 2. But remember, we're defining it as the shortest distance. So the shortest distance from 1 to 3 would actually be going the 1 and then the 2. This 4 is almost never going to actually come into play in this situation. Application, shortest distance. One common application of weighted graphs is on transportation. What is the shortest distance between 2 destinations? Well, if we're going with physical distance, any map is a connected weighted graph and a metric space. If we ignore traffic, we can even estimate time to find the shortest time between 2 destinations by taking speed limits into consideration. If we don't ignore traffic, it becomes a directed graph. We can still do math, but it's no longer a metric space, and so you have to be careful. Note that we're talking about graphs on the surface of a sphere, and so this is, of course, a topology. And that's where the idea of differential manifolds come in. Any differential manifold, any manifold that we can play with, can have a metric put on it, whether it's a donut or a coffee cup. It does not matter what shape the object is. We can create a distance formula. We can create a metric to describe locations on the surface. Here's a practice problem. Consider the graph to the right. What is the shortest distance between A and B? Why don't you pause the video and give it a shot? Mind you, there isn't one set strategy for doing this, but eyeballing it, it looks like the quickest is going to be to go from A to C to D, and then to E, then G to H to B. It certainly is not a direct path, but as far as distance-wise, this would have a distance of 18. And I don't think you can do any better than that. I started it for a while, and that seems the best you can do. But take a look. Can you do any better? Final thoughts. Why do we care about whether or not a distance is a metric space or not? Ultimately, just like with anything else in math, it's a structure, and a fairly common one, which has been studied extensively. I mean, when we think about the Pythagorean theorem, that's been around since prehistory. And so we know the Pythagorean theorem extremely well. What metrics are, what these metric spaces are, is these are spaces which have some distance which works the exact same way as the Pythagorean theorem. And so all of the knowledge base that we have around the Pythagorean theorem, we can then apply to these other metric spaces. This means that when a physicist is trying to understand the motions of a particle, or if they can tie a metric space, they will already have hundreds of years of built-in math to understand that particle. And so we want to try and connect to those whenever we're able to, just so that we can use that huge knowledge base. We just introduced the basics of what a metric space is. If you study mathematics, you would spend probably 2 to 3 years just studying the structures of metric spaces and distances and all of the different applications related to calculus and everything else. And so this simple structure is really one of those foundational structures which describes a large portion of mathematics. And in our day-to-day lives, we can use it to think all the time, but we don't really think about it. When do you have to wake up in order to get to work on time? This is the type of thing which you already know, but you might not think about. You've already mapped out the things that you need to do, and those things that you need to do is really a graph. And so do you need to go to the bathroom? Do you need to brush your teeth? Do you need to eat breakfast? Can you eat breakfast on the way? Do you need coffee? Every single one of these things has some designated time associated with it. And we can create a graph to model all of these different activities. And once we've got that graph, we can then try and figure out what's the best way to optimize our time. We already do this. We do this in our head. We know that if I'm going to get coffee before I take a shower, I'm probably not going to drive to Starbucks and then come back home. I would more likely grab the Starbucks on the way to the office. And so these are the types of things which we already do on a daily basis. We just don't have a structure to describe it. With that, I'll let you get to work exploring where you find metric spaces in your day-to-day lives. Good luck, folks.